Okay, so tell you what, let's do this one together because the one below it is like really similar. It's just you need to know the trick first. So let's do this first one together and then I'll let you practice it on the next one. So I'm going to write down the elements, C, H, and O, and write down how many I have on each side. And then at least maybe try to deal with the carbons and hydrogen. So I think I mentioned this before, but like if you have an element that appears in two different molecules, but on the same side, like obviously they're always going to appear twice, right? Like carbon's here and here. It's hydrogen's here and there. Oxygen though is here and then it gets split up into these two. So when you have it where it's appearing in multiple molecules on the same side, leave that till the very end, okay? So just take a shot at doing the carbons and hydrogens, like add some coefficients to try to make those match. And then let's talk about it. So what number would I put in front of CO2 to give me the, to make the carbons match? Just yell it out. I'm over politeness. 4. Good. Okay, so that makes 4 carbons. It changes my oxygens, but I'm just going to wait till the end and then I'll update them and see what it is. What about the hydrogens? What am I going to do over here? What am I going to put to make the hydrogens match? 5. Okay, so good. 10 hydrogens. So how many oxygens do I have now on the product side? Anybody? How many oxygens do I have on the product side?
7.
Nope. So what did I hit? 13? Okay. Yes, 13. So 4 in front, 2 in each compound. So this one's 8. And then 5 here, but 1 in each. So that's another 5. So 8 and 5 is 13. Okay, how can I make 13 on the reactant side? This is my only place where I have oxygen. I can't, right? I can't get an odd number of oxygens when the molecule has 2. And I can't have a half of a molecule. That's not okay. So I'm going to have to do a little trick to make this work. And the trick is when you realize that this is happening because you have an odd number of oxygens, this happens, it's a stupid like little, if you look at the hydrogens over there, if the hydrogens are not divisible by 4, you don't have to remember that though. But if they're not, this will always happen. So when you see that you've got an odd number of oxygens, I want you to take all of the coefficients so far, not the oxygen, the O2 one, not this one yet, but all the others, and I want you to multiply them all by 2. Okay, so 2C4H10, 8 CO2, and 10 H2O. Now, as long as I multiplied everything by 2, it should keep all the other ones matching. Like the carbons and hydrogens should match now. But let's just double check that they do. So how many carbons do I have on the reactant side? Yell it out. 8. How many hydrogens do I have on the reactant side? 20. Okay. Product side, CO2, I have 8 over there as well. And then H2O, 10 times 2, 20. Okay, so they do still match. Now take a minute and add up your total number of oxygens on the product side. I think it's 20. Is it 26? Oh, yeah, you're right. It is 26. Okay. So 8 times 2, 16. And then 10 times 1, 10. So 26. 16 plus 10. Okay. Now, what do I put in front of the O2 to get 26 oxygens? 13. Good. Okay, so usually what will happen is people will get to the point where they're like, have everything match, and then they see the odd number of oxygens, and then they're like, oh, maybe I should put a 5 there. They just start doing wacky things, and they get distracted and lost and confused. So when you get to that point where you see that you can't get the right number of oxygens because it's an odd number, multiply everything by 2, and then it'll be an even number. All right, so try that with this next one. And if you get through it quickly, you can try the other 2 as well, because we'll do all of these together as well. But I'll set a timer for like 5 minutes, and that should hopefully give you enough time to do all 3 of these. Okay, don't look if you don't want the answer. Okay. So this one, almost the exact same process. You get to the point where you figure out that there's an odd number of oxygens. So you multiply everything through by 2. If you do enough of these, you might start to notice like whatever that odd number is, that's how many is going to be in front of the oxygen. Like you get 25. So then you multiply everything else through by 2, and then 25 goes in front of the O2. So if you want to get to that level of comfort with balancing chemical equations, I just posted on Blackboard under the files. It's like, I don't know, 15 years old, but a worksheet that apparently I made that has 40 balancing chemical equations practice problems and then an answer key. So if you really want to get good, you can do all 40 of those. I would say if you're feeling like, okay, I sort of get this, then just go ahead and do the homework, and that might be enough. If you don't feel like you're at a good comfort level after the homework, maybe go do 1 page of that or something. So I never want to like assign you additional practice problems beyond the homework for a grade. Although it would make you do it, it would also make people do it that don't really need to do it, and it's a waste of time for them. So you just need to gauge if the homework is not enough practice, then you need to go do some of these additional problems. Okay? All right, let's work through the last 2 together. So if you didn't quite get to them, that's okay. If you did, you can just check your answers. All right, so the second one, this is one of those where you want to leave nitrate, NO3, and phosphate, PO4. You want to leave those as a unit. It would get really confusing if you didn't, because then you would have oxygen in like every single compound, and it would just get messy, okay? So leaving them as NO3 and PO4, and I'm going to put parentheses around those just to kind of remind you where they are, the ones that don't have those parentheses in. Okay, I'll add them to all of them to look nicer. Okay. Now I can't see the lead. All right. So when I look at this, it doesn't really matter where I start because there's only one of each in each compound. So I'm just going to start at the top with the lead, and I'll say I'm going to change this to a 3 because I want 3 of those, right? In the process, though, that changes my nitrates to 6. So that's fine. I just need to keep that in mind. I could go over to the other side and start to worry about the nitrates, but I'm just going to stick to this side for now. So I'm going to move on to the sodiums. That's 3 on the reactant side, so I need to get 3 on the product side. That is an annoying way of doing it. It's like kind of rubbing me the wrong way that I have to do this, but I'm going to go with it since that's what I said. Because you guys will make these kind of like, not mistakes, but like you'll do it this way and then realize, oh, that didn't quite help me get what I wanted. Okay, so I'm changing that to 3 on this side. And then phosphate is 1 on the reactant side and 2. Oh, okay, so now I need to go change phosphate over here. I need to put a 2 in front. So do you see why it kind of like bugged me that I started with the sodium? So I did the sodium, but then I had to change it again anyway. So it was kind of dumb that I did that, but like whatever. Sometimes you don't see it until after you've already done it. So now I went back and changed the phosphate so that there's 2 of them. In the process, that changed my sodium to be 6. So now the thing I did on the other side is not fixed anyways. I'm going to go have to fix that again. So that's fine. It's not a problem. Just be aware that it's, going to have to be dealt with. So looking at the product side, lead matches, phosphate matches, and I need 6 nitrates and 6 sodiums. Not like how many more do I need, but how many do I need total. So I need to have 6 sodiums and 6 nitrates. So because they're in this compound, 1 of each, I'm just going to change that number to a 6. And that will give me 6 sodiums and 6 nitrates. And I said something there that I think is probably useful. Don't think always about how many more do I need. Like I had 3 sodiums. Don't think about, oh, I need 3 more. Think about how many do I need total. Okay, I think that might trip you up a little bit if you try to think about how many more do I need. Just what number do I need to change it to so that it matches that total that I have. All right, any clarifications on that one? Another way that you may have done it, and again, you can't always predict this in advance, but I just want to like show you if I'd been doing it and kind of like watching myself a little bit more carefully. So I would do the lead just like I did. I would put the 3 here. When I get to the nitrate, I would probably not mess with it. Simply because, I'm trying to think if I can explain why I wouldn't. I guess what I'm doing in my head is I'm trying to, the numbers that are high on the product side, I'm trying to match those on the reactant side first. And then I'm going to switch over to the other side and try to make those match the reactant side. It's weird because like you get into this habit of like how you do something, and how to articulate what it is you're doing is a little bit confusing. So I'm going to look at the phosphates just because I'm trying to take, these two numbers are high and these ones are low. So I'm trying to get these ones to be increased so that they match over here. So I'm going to do that to the phosphate. I'm going to put a 2 here. And then I also need to write down how that changed the others. So like the nitrate, that made this 6. And the sodium, that made this 6. So then when I go over to the other side, then I quickly know that I need to make this a 6 so that those two match. Okay, so same answer, just kind of like a different order that I approached it in. But as long as you get to the same answer, it doesn't matter. Okay. Okay, last one. NH4 is a polyatomic ion, but it does not appear on both sides. It's only on the reactant side. So do not write down NH4. It won't work because there's no NH4s on the product side. Okay, so just nitrogen, hydrogen, chromium, and oxygen. Be careful too that you realize that like this 2 subscript is for the whole thing. So there's 2 nitrogens and 8 hydrogens. And then the 2 chromiums and the 7 oxygens. Okay, so when I look over at the other side, my nitrogens already match. My chromiums match. My oxygen and hydrogen are off, but I don't want to do oxygen first because that appears in 2 different compounds. So I'm going to do the hydrogen first. So I'm going to put a 4 here. So that changes this to 8. And then in the process, it actually changed my oxygens to 7. Because I had 3 from this compound and 4 from that compound. So it fixed it without me actually trying. So another good reason not to mess with something when it appears in multiple compounds until you have to. Okay. Any clarifications? Lots of practice. Okay, so, I was going to write the answers down for these. Let me just do this real quick so you guys can write them down. And if you want to check your answers later, try to write them somewhere where it's not like you're going to see them, obviously, or else it's not going to be a whole lot of practice. SO4, 4, okay, so... I just did this one earlier. What did it end up being? This, I think? Yeah. Okay, so if you want to write those down or take a quick picture so you can use that as some practice later as well. Okay, so what do these balanced equations mean? Well, we showed pictures at the very beginning of this that showed the molecules. I'll scroll up to one. There. Showed the molecules so that you could see, like, we're not changing the overall number of atoms. We're just rearranging those atoms, right? So the number in front, the 2, represents how many there are of that molecule. There's 2 oxygens or there's 2 H2Os. It's weird when we say oxygen because we mean, like when I say 2 oxygens, in that context I meant 2 oxygen molecules. There's 4 total oxygen atoms though. Those diatomics will get you every time. Okay, so 2 water molecules. So yes, they definitely mean the number of molecules. It's important, though, to understand that they can also represent the number of moles of molecules. I don't know why it always bothers people when we talk about moles, because if we talked about a dozen, I don't think it would bug you. If I said a dozen methane, 2 dozen oxygen, 1 dozen CO2, and 2 dozen H2Os, like that is the same ratio, right? 1 dozen is 12, 2 dozen is 24, 12, 24. So we're saying this could mean 1 CH4 reacts with 2 O2s, but we could still apply that ratio, and that would be the same ratio if we said 12 for every 24 O2s, right? So using a mole is the same thing. Saying 1 mole of CH4 molecules and 2 moles of O2, we're just scaling up that ratio. 1 mole of CO2 and 2 moles of H2O. We're just scaling that up so that it's on a scale that we can measure. We can't measure a single molecule, but we can measure 6.022 times 10 to the 23rd molecules. That's much easier for us to measure. In fact, we've worked out chemistry so that it's 12 grams for every carbon. So we know that CO2, a mole of CO2 is going to be 44.01 grams. We have worked out this system so that it's easy for us to measure a mole of CO2, even though we can't measure a molecule of CO2. Okay? So the coefficients in front represent how many molecules, or we can think of them as the mole ratio as well. So what we need to do now is figure out how to do calculations with those mole ratios. So stoichiometry is this weird word. It basically just means doing a calculation using the mole ratios from the balanced equations. So keep in mind that this in text here, that's like me verbally writing it out in words, what that balanced chemical equation means. This one in terms of molecules and this one in terms of moles. Okay? They're equivalent in the sense that they are both correct. This is usually what you imagine in your head, and this is what you would actually be able to measure in real life. Okay? So because we can apply it to both of those, every little combination of 2 can turn into its own little ratio. And this is where people start to get lost. So we're going to use an analogy. I've used banana smoothies in the past, and your book uses pizza. So we're going to go with pizza. Okay? A balanced chemical equation is just a recipe for how to make something. Sometimes we care about the thing that we're reacting. So like in the octane one, this is octane, which is the primary component of gasoline. So we burn gasoline with oxygen. It produces CO2 and water. We actually care about the heat that comes off. Well, in gasoline, we actually care about the gases that expand, but whatever. There's a lot of heat that comes off, so that's the thing we care about. If you're making a drug or plastic or something, you care about the product that's coming off. Sometimes you just care about getting rid of the thing you're burning or the thing you're reacting. You're like, oh, I have this toxin that I want to break down. So you're trying to get rid of the product. In a recipe, we always care about the thing we're making, right? So in this example, we're making pizza. And we have this recipe that tells us the exact ratios of ingredients that we need to make a single pizza. So we're going to do some ridiculously easy calculations, but we're going to do them the long way with dimensional analysis and conversion factors so that you guys get used to doing it so that we can do it for a balanced chemical equation. Okay? I'm not going to use the one that's down here. I want to do a different one because they already have it written out. And sometimes I feel like you don't pay attention if it's already written out for you. Okay? So I'm going to make one up. Let's say, we'll use the 10 cups of cheese still, but let's say how many ounces of sauce do I need to react or to like mix into the other ingredients with 10 cups of cheese. So I'm still going to use that 10 cups of cheese, but instead of asking how many pizzas I can make, I want to ask how much sauce do I need with that 10 cups of cheese. So this isn't that crazy because maybe you like have chocolate chips and you really want to make chocolate chip cookies, but your limiting factor is the chocolate chips. So you're like, okay, if I want to use up all the chocolate chips, how much butter do I need? How much flour do I need? How much sugar do I need to make the maximum number of cookies with this 1 cup of chocolate chips that I have? Okay, so that's kind of what we're doing here. We want as many pieces as possible with that 10 cups of cheese. How many ounces of sauce do I need for that? Okay, so I want you guys to try to set up a ratio that's going to describe, like just like this one down here, set up a dimensional analysis problem, determine a conversion factor from that recipe. Okay? So same thing we've done always before. Look at the unit of the thing you're trying to get to and the number and the unit you're starting with. Okay, so I'm starting with 10 cups of cheese. I'm looking for ounces sauce. So just like I've done in every 90% of the problems in this class so far, I'm going to put the unit of the thing I'm trying to get rid of on the bottom. Cups of cheese. I'm going to put the unit of the thing I'm trying to get to on top. Ounces sauce. And when I have those two together, I'm going to go to the recipe to figure out what that ratio is. 5 ounces for every 2 cups of cheese. So I'm going to put that in my conversion factor. 5 ounces for every 2 cups of cheese. 25. Great. Now, the example they showed was with that 10 cups of cheese, how many pizza can you make? Okay, so same thing. Cups of cheese on the bottom, pizzas on the top. You look at the recipe, 1 pizza for every 2 cups of cheese, 10 divided by 2, 5 pizzas. Okay, so we're going to take that same approach, but with a balanced equation. Yeah. The recipe, yep.
Which is our conversion factor.
Yes, exactly. These are your conversion factors, and the analogy is this is what a balanced chemical equation is going to be when we start doing it with chemicals. So every time we get like confused about a balanced chemical equation, I'm going to be like, it's the pizza. How much cheese do you have? How many crusts do you have? We're going to go back to this analogy, okay? So I feel like I'm beating a dead horse if I make you guys do this. Oh, look, that's like the exact question I just did. So we'll skip that. Okay, let's skip from the analogy. Let's go to a real chemistry problem, then we'll come back to it as needed. Okay? So let's go back to the octane equation. And I want you to, at the very least, just set up the calculation. If you feel like I don't even know what numbers to put in here, just worry about getting the units in the right place for this one. Okay, so I'm going to let you take a look for a minute. And if you need to, look back at the pizza example and do the same thing for this one. Oh, I forgot the roll again. Okay, so cross out the 26th. Because I didn't send it around. Okay, so the unit that you're starting with, the number and the unit you're starting with is the 22 moles of C8H18. You're trying to get to moles H2O. Okay, so again, same exact process. Moles C8H18 goes down here. Moles H2O goes up there. All right, just like we have talked about having this list of conversion factors, mental list, actual list. Every time you see moles of one compound and moles of another, this is the first time we've seen moles and moles together. Well, not the first time. We did it with like moles of an atom in a molecule. Very small example. We've rarely seen moles and moles together, okay? Moles of one compound, moles of another. I want you to go, balanced chemical equation. Just like when you had grams and moles together, you want to think periodic table, okay? When you have like some metric prefixes, I don't know, micrograms and grams, you want to think what's the metric prefix. When you see moles and moles, balanced chemical equation. So you just put the coefficient 2 there and then water 18. That's it. Okay? So you need to set up the part of the equation, then you need to worry about what numbers go in there, and the numbers come from the balanced chemical equation. So 198 moles of water. Apparently on the next slide, I just duplicated it. So let me rewrite it and like give us another problem that's different than what's written there. Okay. Let's say determine the moles of, let's use the 22 moles, but let's say determine the number of moles of O2 that are used. So the wording's slightly different because now we're not asking how much stuff is made. We're saying how much sauce we need for a given amount of crust, right? We're saying how much oxygen is needed in order to react that 22 moles of octane. Because you can't just put octane in a container and think that it's going to burn. It needs oxygen in there for it to burn. So we want to know how much oxygen, how many moles of oxygen. Okay, so if you're still trying to follow what's going on, I'm going to set up the calculation again, at least the first part of it. All right, so moles and moles, pull the coefficients from the balanced equation, 2 and 25. And what does it come out to be? Have you done the math? What was that? 275? Okay. Okay, so every time you see moles and moles together, you're looking at the balanced equation. Now, are we actually going to be asking about moles of C8H18? Probably not. Most of us are going to measure gasoline, octane, in gallons. So maybe we're going to have to like convert to moles somehow. So literally for the rest of the semester, yes, we'll do other parts of gases and other parts of solutions and stuff, but lots of the time, we're going to be trying to get to moles in order to be able to use the balanced equation. So maybe we have like grams of octane, which is also unlikely because, you know, we measure it as a liquid. So maybe we end up having, I don't know, gallons, liters, something like that of octane, and we have to use we don't know what molarity is yet, so I can't use that as an example. Let's just pretend it's grams. So maybe we have grams, and we have to use the molar mass to first convert it to moles, then we can use the balanced equation. So a common theme you're going to see is whatever you're starting with, convert it to moles, then do a mole-to-mole conversion. So maybe this is like, we'll call this X and Y. Some compound, convert it to moles, then convert it to moles of the other thing, and then convert it back out to whatever you're looking for. So maybe this is grams. Maybe it's liters of a gas. Maybe it's liters of a liquid. There's all these different measurements we can start with, but we can't use the balanced equation until we're in terms of moles, okay? So we will literally spend the next week, like this is the only topic, there's little add-ons and little practice we need to do, but like Wednesday, Friday, Monday, we're gonna be practicing all the variations on this idea of using the balanced chemical equation, okay? All right, so we'll stop there and pick it up on Wednesday.